Okay, so we're about to hit the halfway mark. Hard to believe. Um, so next week is when I head off to uh, London for a conference. There will be class on Tuesday, and then shortly after that is when I have to get out of here. We will not meet for the next 3 sessions after that. That's posted on the site on the lectures page. So what I will try to do during that stretch is record things for what I need to cover or answering questions of general interest and posting those so that things still move along as much as possible. Now, I'm not sure how much I'll have for today because yesterday I was trying to code up something to demonstrate for you all and couldn't get it to work. It was involving graphical user interfaces, and so things were going well to a point, and then what I also found is that the various online tutorials are not as helpful as you'd think they would be. There are so many of them, but to even perform rudimentary functions, it was difficult to like for some cases, like setting up menus and so forth. There's plenty of examples out there. That part is easy, but as far as getting a functionality behind them implemented, it's never matter. And so I think what I'm going to do is I still want to do something like that, but it's something that I would need to take more time to try to prepare. Find some, also try to dig up some better resources that you could use also. And maybe after I return, because once I get back, we'll have 2 weeks left of class, and I can fit it in there. Also, it's a good idea for when you're making graphical user interfaces. You don't have to, but it's a good idea. So they say to work with classes, so that gets into object-oriented aspects. And that's something I'd want to take more time on, but just trying to fit it into one class. So, so hopefully that can work. I did prepare a backup activity. That was a lot safer. So I will have that for you. And it'll be a preview of what I have in mind for like a default project if you're unable to come up with one that you yourself would be interested in doing. Although, after yesterday's experience, reluctant to say exactly what I have in mind, just because, what if I can't get that working either? But if I can, it'll be really cool. I think my chances are a lot better. So that's something I'll take over weekend. So hopefully on Tuesday, I'll be able to say something more about that. Now, the first assignment. So I've received submissions from half a class. No, I've not looked at them yet, but hope to soon, like next couple days or so. But what I'm getting questions on is measuring the order of accuracy. And so what I'm going to do now is show you how that's done, because I'm going to do it now on my own solution. So that way you can see what numbers you're supposed to get, and if they're not matching, then you can then you'll know if any of your methods are implemented incorrectly, and also which ones. Now this is for methods that are of order 4. So there's 4th order Brancacutta, the 4th order Adams Bashforth method, and the 4th order Predictor Corrector method, all of 4th order. For lower order, of course, is 1st order, and then we don't really have an order of accuracy for ODE 2.3 because it's adaptive. It doesn't use a fixed time step. But in general, it's meant to be at least 2nd order. Now, okay, so we haven't. So what I can do is for these 3 methods, we'll get that to work. Okay, I need to restore my font size. Okay. All right. So, so what we have here, and I'll post this later. that, and I realize I'm giving away portions of a solution, but not the meat of it, so it's okay. Now, so here, for instance, I'm using, this is a predictor corrector method on the first scalar ODE, so y prime is equal to minus 2ty, and then computing two solutions of different h's, time steps, so 0.1, and then we cut it in half, 0.5. So because these are four-polar methods, if you reduce the time step by a factor of 2, then the error should reduce by a factor of roughly 16. Now, it's not going to be exactly 16. I can tell you that already. But it should get closer and closer to that factor as h goes to 0. But it also depends on the time interval, because the actual error in these methods, the local truncation error, is the appropriate power of h times some higher order derivative of a solution. So for a four-polar method, it would be the fifth derivative. Evaluated at an unknown point during that time step. Now, as h goes to 0, then that unknown point has less and less leeway. So, but that's why there's some fudginess in the numbers here. It's not really going to be 16 necessarily, but should be in the ballpark at least. Okay, so now I'm computing the solution for first scalar ODE and then the exact solution by passing the time values, to my exact solution 1 function. And then I do the same thing for the system of ODEs with the same time steps, and take those t values and call exact solution 2 with those. And then for measuring error, so I'm comparing each computed solution to the corresponding exact solution, and taking the infinity norm of the difference. So this is just making NumPy ND arrays from these solutions that are just, the solutions are lists. So then we, after we get all these infinity norms, then for the errors from the first problem of a scalar ODE, I divide those errors. So order 1, order 2, actually it's not really the order that I'm showing here, but it's the ratio of errors, and it would give me an idea of the order. So what I'm going to do, in fact, okay, so if we assume, I like to actually see what it thinks the order is. So if the error as a function of h is approximately some constant c times h to the p, so therefore error h over 2 is the same thing, except h over 2 in place of h. So now if I take the ratio of errors, so the c's will cancel out, which is nice. So of course we're going to get 2 to the p. So p is therefore the log, log to base 2 of this ratio. So actually natural log of ratio divided by the natural log of 2. So let's do that. Okay, I'm importing math already. So if I do math.log divided by math.log of 2 and do the same thing for the other one. Okay, and then print these out. Okay, so all right, actually, I don't want to do this method first. I want to do RK4 first. But yeah, this was actually scripted. I tried this out before I came in here. I was going to set myself up for embarrassment or something. Like, oh, this method isn't converging at all. Okay, so fourth order. Okay, So these are pretty dang close to fourth order. So for the scalar ODE, 3.99, rounding up, and then 3.91 for the system of ODEs. So that went well. And then we'll do the same thing for the Adams-Bashforth fourth order method. Okay, so actually, let me put that back. Okay. I'll label these so when I post the log later. Okay. And now, as Bashforth, and I got to change all four of these. As Bashforth 4. Okay, let's see how that does. Okay, not as close, but pretty decent. Definitely closer to fourth order than third, so we'll call that a success. And finally, the fourth order predictor corrector method. Oh, slightly greater than 4. That can happen. It's allowed. Because again, depending on these unknown values of the derivative. So that's quite nice that that happened. And the only other one that I can do whoops, don't want to do that. Forward order. Yeah, I couldn't remember what I called it exactly. Okay. Now this is supposed to be first order accurate. Might as well make sure of that too. Oh, that's bad. Then again, so the error actually seemed to increase from one to the next for the second problem. The other one's like very close to first order accuracy. But we also recall that even for a first one, that the error could actually be seen on the plot. That it wasn't all that that accurate. Now, if I were to change this time step, cut it by a factor of 10 for both, so it's still being cut in half. Let's see if okay. I wonder if I was. I have been doing some tinkering, and I wonder if I might have messed things up when it came to this case of a system. When I was trying out various things to talk about in class. I need to make sure of that. Okay. Oh. Yeah, that would be a problem. Doing the plus equals there. So yeah, that's something we had discussed earlier. So, okay. Let's try this again. Okay, now it's first order. Like, I knew it had to be something like that. It still happen as h goes to 0. So, code can be screwed up anywhere. And a valuable lesson to come from this, because this is one of my weaknesses when it comes to coding for my own research, and that is I will get something working, so satisfied with it for purpose of like putting results in the paper or something like that, and then I'll continue tinkering with it, maybe breaking it, and then forgetting that I tinkered with it, and then when I return to that code months later, it's like, what did I do to it? So when something's working well, back it up. Yeah, I mean, I have a zillion copies of my code, especially for KSS methods, all over the place. So I definitely have something to go back to. But
well, you also got it online, so worst case scenario,
yeah.
Zombie apocalypse. I think you'll still be able to find KSS.
Well, actually, the KSS code is posted on my webpage is very limited in scope. But yeah. But also, I've emailed it to so many of my students, and yeah, it's out there somewhere. Okay, so any questions about measuring the order of accuracy of these methods? Okay. So after class, I'll post this code snippet and also the valid results here, um, and so that you'll have something to compare with it. Now, if you've already turned it in, but then you go ahead and try this, and you find that your numbers don't match, maybe there's something wrong. That's fine. You can go back and fix it and resubmit. Because it won't be until the weekend when I would start looking at these things anyway. But it'd be a good idea to check that on your own code sooner rather than later. Okay. So moving on, what I have in mind is sort of a combination of things that we've already been playing around with, because he had one assignment that dealt with time-stepping methods for ODEs, and the second assignment deals with solving system linear equations, working with matrices, including finite differences to solve a two-point boundary value problem. So now I want to try to combine the two for solving time-dependent PDEs. So you'd be using spatial discretization for approximating the spatial derivatives, like UXX in the heat or wave equation, for example, and then so then that would involve a matrix that represents a differential operator, such as the Laplacian, and then that would handle spatial part. For the time part, you would discretize your time derivatives and end up using these same kind of time-stepping methods for ODEs that we've been looking at. So in other words, you discretize your PDE, get a large system of ODEs, so containing many equations, and then use these time-stepping methods for ODEs to solve that. Okay. So we'll start off with a simple problem to look at. Okay, and since I'm not very concerned about time right now, at least I can take time to talk about both the mathematical and coding aspects of this. Those of you, well, actually, only two of you in the room, and then maybe a couple of remote students took my 721 class from last year. So that part will be familiar. Okay, so we're looking at the heat equation in 1D, and working on a interval 0 to 1. Okay. And then I'll impose initial condition, and boundary conditions. And here are simple kind of boundary conditions. Homogeneous Dirichlet boundary conditions. So we're specifying that the value of a solution at both endpoints of a spatial domain are 0. As opposed to, for instance, Neumann boundary conditions, where we impose conditions on the first derivative with respect to x, or also periodic boundary conditions, or a combination of Dirichlet-Neumann called Robin or mixed boundary conditions. Okay. Now, what I'm going to do is specify a grid on the spatial domain, interval 0 to 1. So I'm going to specify a certain number of grid points. We'll just use 100 in this case. And then we'll use a spacing dx for delta x. Okay, so the idea is we have x equals 0, x1, x2, so forth, xn, and then xn plus 1, which is equal to 1. So here are your boundary points, and here we have n interior points. But because there are n interior points, we have n plus 1 subintervals. So that's our spacing. So we have dx in between all of these. Okay. And then what I could do is, I'm gonna, first instance of needing numpy, I'm going to create a vector of x values. So I'm going to make that an array. Okay. Oh, whoops. Sorry, using MATLAB syntax there. Whoops. Okay. So and note that I'm using the open interval here, 0 to 1. I'm not including boundary points in this because these are the x values at which we're computing the solution. We already know what the solution is on the boundary points. It's 0. Okay, what is it complaining about? Oh, import numpy as np. Forgot about that. Okay. Always watch over here. If it's complaining about something, usually, not always, usually there's a good reason for it. Okay. Next, we have the for spatial derivative, because we're in the process of obtaining a system of ODEs from the PDE. So what we have here is a most often used for this is the center difference. All right, so the approximation I'm going to use is uxx approximated at xj. I'll say equal to because I'll account for the error also. So we have 1 over dx squared times u xj minus 1 minus 2u xj plus u xj plus 1 plus an error. So this is a second order accurate formula. Okay. Now, so what ends up happening here is, if we think of this as a matrix vector product, then the approximation of second derivative at each point, if you think to define a vector of u values of u at all the equally spaced grid points, this is one element of a matrix vector product. So the coefficients of the u's here, or combining these u's to get linearly to get approximation of uxx, define one row of the matrix. And since we're evaluating xj, and here we have u of xj, minus 2 is a diagonal entry over dx squared. And then we're using neighboring points. So we have a 1 on the subdiagonal entry, and another 1 on the superdiagonal entry. So the differentiation matrix in this case is, I'll just go ahead and write the code for it here. So we have 1 over dx squared times, and I need sparse matrix functionality now. So import scipy.sparse as sp. So now I can use sp.diags, and my entries along my diagonals are 1, minus 2, and 1, which, as I've mentioned a couple times before, I'm using broadcasting of scalars, that these numbers will be copied to every element of their respective diagonals, and I'm placing them on diagonals minus 1, 0, 1. And I need the matrix to be n by n. So that size is required when you're doing broadcasting. Okay, so what's happening is this matrix times a vector that represents values of a function on the grid will return another vector that is approximation of a second derivative at those points for the case where the boundary values are assumed to be 0, which they are for the solution. So otherwise there need to be an extra term with boundary values. Okay. Now, I'm going to define my spatial differential operator. If we keep in mind that the heat equation we're using here is du dt is equal to c squared uxx. We need to multiply by L is equal to c squared. Oh, I need to specify a value of c. For now, I'll just say 1. Times d2. So d2 represents the second derivative, and we're just multiplying by this coefficient. Okay. So as a result, the system of ODEs is u prime of t is equal to LU of t, where u of t is the components are functions of t now. And I'm putting a transpose in here because we're going to, since L is an n by n matrix, u of t must be a column vector. And this approach is called the method of lines, where we have, so your solution u of xt is now represented by n functions, one corresponding to each grid point. So the idea is that uj of t is an approximation of u of xj t. All right. And then we need an initial condition for a system of ODEs. U of 0 is equal to vector f, where fj is equal to f of xj. So whatever initial data we have, we're going to evaluate it at all of the grid points, all the elements of this x here, and get a vector. Oh, that's a column vector, so that should also be transposed. Okay. Now, what I might as well do at this point, now that I have, so my system of ODEs is defined except for, I need an actual initial condition. So I have this initial condition here, u of x0 equals f of x. I haven't said what f is. So I'm going to make up an f. So I'll define that in Python here. So I'll have lambda x. So math.exp. I could use a define also, but seems a bit much for a one-line function. So it's a Gaussian function. So e to the minus 100 times x minus a half squared. Now, the reason for x minus a half is this function is defined on 0, 1, on the interval 0 to 1. So I want a peak of a Gaussian to occur in the midpoint of that, x equals 1/2. So I'm performing this shift, like they teach about in college algebra, I guess, of graph transformations. Okay, so now, that I have my f, I'm going to initialize my solution. So I'm going to use a variable u to represent my solution. That's a vector. So I'm going to evaluate f at all the grid points to get my initial solution u. Now, it would be lovely if I could do f of x, because I have f and I have x, but I can't do that. As I've mentioned before, I have to vectorize. So np.vectorize f. So then this whole part that I've highlighted is now itself a function handle that what it will do is it will evaluate function f at all elements of whatever is given to it, in this case x. So from here I'll have my initial solution. Okay, so now the system of ODEs I need to solve as a result of spatial discretization is completely defined. And why is it still complaining here? Oh, I forgot to import math. Okay. Now, the boundary conditions are automatically taken into account by how a matrix is set up. Because if I so for instance, if I let j equal 1, so j equals 1 is the left boundary, j equal n is the right boundary. So if I go ahead and put this in here, but account for the fact that j is equal to 1, so then I have x naught, x1, and x2. But x naught is the left boundary point, x equals 0. Well, the solution is 0 at that point. So, so I can just cut that out. Similarly, I can look at the right boundary point. So I have j equal to n now. And xn plus 1 is the right boundary point, which is equal to 1. And the variable solution is also 0. So in this case, this is all we need to approximate the second derivative. We don't need any other terms. So so the matrix vector multiplication accounts for the entire approximation of the second derivative for both interior and boundary, for all interior points. On the other hand, if I had non-homogeneous boundary conditions, like u of 0t is equal to something, non-zero, and u of 1t, I would have extra terms in here, and those could not be included in the matrix vector product. So that would result in a system of ODEs like u prime is equal to LU plus some other term that includes boundary values. So that's one thing to keep in mind. That yeah, this problem is very much watered down. Okay. Now, all right, any questions up to this point? All right. Now, for time stepping, now I'm going to focus on the simplest methods here, like first or second order accurate. But even then, there's some interesting issues to discuss. So the time-stepping methods we'll look at are, as you know, familiar with forward Euler, first order accurate. So that is u n plus 1. So I can use a superscript to refer to time values, as I'm using a subscript to deal with spatial subscripting. Plus dt times the matrix L times un. So this method is explicit. Then we have backward Euler, also first order, implicit. Although what I can do is rewrite this as identity minus, if I take this term and move it to the other side and factor out a u n plus 1 on the right, then I have un on the right side. I can express forward Euler in a similar way. Here I can factor un out on the right, and I get identity plus dtl. Okay. Now, one thing that's worth pointing out about these, and actually, you know what? I didn't get this far in 721. I did cover time-stepping methods for ODEs, but never really put it all together. Okay. If you recall the Taylor series for the exponential, what we have here are the first two terms. So identity plus dtl is a first order approximation of e to the lt. And it's worth pointing out that the exact solution of at least a system of ODEs is e to the lt times f. So this is how we can see that Euler's method, forward Euler, is consistent with the underlying system of ODEs, that it's a legitimate approximation of the exponential. Whereas with backward Euler, is a first order approximation of e to the minus lt, but it's on the other side. So if I were to multiply by the inverse, then I'd have un plus 1 is equal to, oh, actually e to the l dt, not t. So by moving to the other side, having the inverse of this, I'll just write it out here. First order approximation of e to the l dt again. So we see both of these are would work as delta t goes to 0. Is that we're using different approximations of the exponential. Okay, and then number one, Crank-Nicholson. So it's actually literally averaging the two. So I have, so this is second order implicit. So so Crank-Nicholson is a method as applied to PDEs, but if you're talking just about time-stepping methods, based on the implicit trapezoidal method for ODEs. So we have a un plus dt over 2 times lun plus lun plus 1. So it's averaging for right sides of what you get from forward Euler, lun, and then backward Euler, lun plus 1. So if I were to rearrange this and put in the same matrix vector form as the others. All right, and then what I'll do is on both sides I can do some factoring. Oh, whoops! I forgot the dt over 2 there. So on the right side, left side I factor out un plus 1. On the right side, I on the right side, I factor out. Dang it. Un. Okay, so on the right side we have one approximation, the explicit kind of e to the L delta t over 2. And then here we have the implicit approximation of e to the minus L dt over 2, which then is then inverted. So now we have yet another approximation of e to the L delta t being multiplied by un to produce un plus 1. Okay, so all three un plus 1, some approximation of e to the L delta t times un. Now, the reason Crank-Nicholson is second order accurate is that because of the symmetry of it, is leading to cancellation of the error terms that are of order delta t. So if you did a full-blown error analysis to look at the local truncation error of all previous methods, which I won't do here because this is a Python class. If you really want to do that, though, knock yourself out. Those terms would cancel, leaving the leading order term being a order delta t squared. Okay. All right. Now, okay. But another thing is, that relates to these methods is you can actually express all three of them as one method with a parameter. So the this form, identity minus theta times dt times L un plus 1 is equal to identity minus 1 or plus 1 minus theta dt times L un. Where theta is some parameter between 0 and 1. So for example, if I say theta equals 0, that is forward Euler. Theta equals 1, the opposite extreme is backward Euler, because then you'd have nothing over here except un. And then finally, theta equal 1/2, that is Crank-Nicholson. Okay. Now, can be shown that this time-saving method is unconditionally stable if theta is at least equal to 1/2. So anything ranging from, as soon as theta is non-zero, it's an implicit method. You have to solve some system of linear equations. But the larger theta is, you end up being able to you don't have to worry about the time step. You can choose the time step as large as you want, and the solution will at least remain bounded. But for the forward Euler case, you must have c squared delta t over delta x squared less or equal to 1/2 for stability. And so this is the CFL or Courant-Friedrichs-Lewy condition. And that's a pretty severe restriction. So what this says is, if I shrink delta t by a factor of 10 in the interest of getting more accuracy in time, I need to shrink delta x by a factor of 100. As opposed to the wave equation, there's the CFL condition in that case relates delta t to delta x to the first power, so it's not nearly as restrictive. This is one reason why it's generally advised not to use explicit methods for parabolic PDEs such as the heat equation, because you'd be taking a zillion time steps. So for example, let's figure out what the time step should be. If I say c equals 1, n is equal to 100, and then dx is 1 over n plus 1. So if I rearrange this, I need dt, I must have dt less than or equal to 1/2 dx squared over c. So if I figure that out in this case, I must have, so for only 100 grid points, which is not that many, so 1/2 times dx squared, and c is 1 in this case. So that's how small my time step has to be. Dang. So roughly 5 times 10 to the, so 0.00005 for only 100 grid points. Otherwise, my solution will grow over time. It'll blow up. And since I'm too lazy to do this in my head, okay, well, I did get it right, but still, I'd say 20,000 time steps. And the thing is, a lot of researchers that have a working knowledge of numerical methods, just enough to be dangerous or detrimental to themselves at least, and their own productivity, they'll just say, oh, I'll just use forward ladder because it's so easy to code up. Or maybe even 4-forward run kata, but 4-forward run kata is an explicit method. It's highly accurate, but it has a similar stability restriction. So then they're taking a zillion time steps when maybe they could solve a problem with decent accuracy so much faster, hundreds of thousands of times faster if it's a large-scale problem. And people don't think about that, unfortunately. So they need to be educated there. Okay. All right. Actually, let's see. What about? Let's see where I'm at here. Okay. No, I'm gonna take my first break at this point because. Okay. And then so actually code up this unified time stepping method. We'll take a look at the behavior, because the behavior, when you like plot solutions and so forth, is pretty interesting as well. Okay. So now I'm going to compute and plot the solution as we go. So now I need to import package I need for plotting. So import matplotlib.pyplot. And I'm going to be solving a sparse system of equations. So for that, I need scipy sparse.linalg. Call it SPL. Okay. Now, I've typed a lot of junk here. Not done a lot. Okay, so I want to plot the initial data. So I'm going to plot the solution after every time step, beginning with the initial data. I want to have it pause in between time steps. Now, like in MATLAB, you would just use the pause command. I also have been too lazy to look up whether there's an equivalent in Python. There probably is, but I don't even need one. I can just do this input, and I'm going to put a message here. Hit enter to continue. So then I can just hit enter, and it'll go from there. So that will simulate a pause. Now the number of time steps. Okay. Well, first I need to set a final time. I didn't even specify that. Did I? Okay. No, I didn't earlier. So I'll just set capital T to be my final time. I'll just let it be equal to 1. And then the number of time steps would be, I'll use n steps here, is t over dt. So actually, did I? I don't think I've set a dt either. No, I'll do that in a moment. So I'll just do that right now. Let's just say 0.1. Okay. Now, in that case, the number of time steps is going to be 10, but I want to be sure it's an integer. So, because there could be round off error and so forth. So, you may have noticed for when running your first assignment, you're looking at the time values that are displayed, like using a default time step of 0.1. As they starting from 0, adding 0.1, 0.2, 0.3, 0.4, but it's not exact because you get something like 0.6999999 because of round off error. The number as simple as 0.1 cannot be represented exactly in IEEE double precision floating point system, so that's bound to happen. Whereas something like a negative power 2, 1/2, 1/4, 1/8, those can be exact. Okay, so now I can do a for loop. Take this many time steps. Now, what I need to do if I'm going to set a theta value. Theta equals, or did I didn't set it earlier. I'll do 0.5 for Crank Nicholson. Okay, and so the way this works is, if I go back up to where I defined a method here, I have my solution for a previous time step, un. I need to multiply it by this matrix, identity plus 1 minus theta dt times L. And then that's my right-hand side for a system of linear equations where un plus 1 is the unknown. And then this, identity minus theta dtl, is the matrix of the system. So these two matrices, this one on the left, this one on the right, I need to form these because I'm going to be using them every single time step. And I should do that outside the loop. Okay. So what I'll do is, two matrices, m left, I'll call them m left and m right. So it'll be, I need a sparse matrix. So sparse dot identity n by n minus theta times dt times L that I defined earlier. And then on the right side, I have identity plus 1 minus theta times dt times L. So now my matrices are set. So now I can carry out my time step. So I'm going to use a sparse solver with a matrix m left, and the right-hand side will be m right times the previous solution. So the solution will be overwritten with the new one. Okay, and then I'll go ahead and plot it, and also indicate that it's paused. So, okay. All right, and we're ready to rock. So any questions about the... Okay, so everything I typed since the break is, at least can be seen on the screen now. So any questions about what I have here? Yes?
So the I function will actually take a single entry to make a square matrix, whereas other matrix ones you have to enter both of them. The default is a single. The default is in one instead of one matrix.
I mean the arguments.
Yeah.
Yes. Yeah, it's kind of weird how it's different than the other functions. Yeah, that it behaves more MATLAB-like. Yeah. Yeah, it's kind of strange to confirm by the documentation. Okay. Any other questions? Okay. All right. Now, make this a little bigger so I can see better. Okay, so right now it's set to use Crank-Nicholson, and assuming I didn't mistype anything for my notes. Okay. Okay, good. This is the initial data that I created. I want a Gaussian function that was fairly concentrated, because the heat equation has an effect of smoothing out the initial data, even if it has like discontinuities. Just as if you have some heat source, as it warms up the room, the temperature smooths out to a constant average temperature over the entire room, given enough time. So that's the sort of thing we're going to see here. But there's going to be some weird behavior here. Notice it kind of flipped like that. That seems odd. And then, so this is at time equals 0.1, and then I'm going to keep going. Now it flips back, and then, so that's seems kind of troubling. You wouldn't expect temperature to behave like that. Okay, and now it's finished. But what we're seeing here is that the plot is not as just looking at the curves is not very informative, because if you look at the initial data, all right, I picked a Gaussian. I didn't scale it or anything, so the initial values are between 0 and 1. But if I go all the way down to the end, okay, so the notice the vertical scale, minus 0.05, or actually more like a minus 0.1 up to 0.15. It's contracted a little bit. Now that is expected because the solution should smooth out to a constant. In fact, this will eventually, because there's no reaction term in this equation, the solution will decay to 0 eventually. So, well, actually, even if there was a reaction term, it would decay to 0. But there's no source term to keep it from going to something non-zero. So I want to better show the behavior of a solution over time, I want to have all of these plots have the same axis limits. So in each one, I'm going to stipulate, I'm going to use some functions I haven't used before in plot, in this class anyway. Xlim and Ylim can be used to set, so it's similar to the axis function in MATLAB, but you have one for X and one for Y. So I'm going to set constant fixed axis limits, 0 to 1 in X and minus 0.5 to 1 in Y. And I'll do that for each plot. Okay. So then, as the solution decays, we'll actually be able to see that. So now if I go again, all right, so that's where we're starting out. And as we saw before, it flipped. So there you see it. And it's flipping back and forth, but less pronounced because of the diffusion causing the exponential decay of all the components of a solution. Okay, and that's where it stops. Okay, so that behavior still seems kind of non-physical. You wouldn't expect the temperature to oscillate like that. So what I'm going to do is, there's a couple different things I can try. One is I'm going to shrink the time step. Let's just cut it in half, 0.05. That alone will decrease the error by a factor of 4 because it's a second order method, but let's see about the behavior. So now it's going to take 20 time steps. And yeah, unfortunately, it's still flipping, so that's kind of sad. Maybe not quite so much. So in fact, if I promise to go through time steps really fast and shrink it down to 0.01, so that's going to take 100 steps, but I'll just scroll through them quickly. It's kind of like a movie in a way. It is less pronounced, noticeably, than before. So that's one thing to keep in mind. That the larger time step seems to have something to do with it. Okay, come on. Have to get through 100 time steps. At this point now it's just boring. Okay, now the other thing I want to try that I can vary is the choice of time stepping method. I had theta to be 0.5 for Craig-Nicholson. I'm going to change theta to 1 for backward Euler. Let's see if the same thing happens in that case. Even though it's going to be less accurate, it's only first order rather than second. Okay, there's the initial data. And notice it doesn't flip. It just steadily decays to 0. Okay. What if I do something in between, like 0.75? So it's not a named method. It's implicit. It is unconditionally stable. Let's see if we get some effect in between. Kind of, yeah. But it goes away pretty quickly, even after 10 time steps. It's not nearly as much. So that's good to know also. On the other hand, what if I change it to theta equal to 0? That's forward Euler. My time step is 0.1, which is a bit large. So, yeah. It's going all outside the window. It's blowing up. So, yeah, that's a disaster. But what I have to do is, in order to, as I showed you earlier, in order to have this solution be bounded for forward Euler, I need to take 20,000 time steps, which I'm not going to do. Okay. So now I'm going to show you why why are we getting a strange behavior from Crank-Nicholson, which is the most accurate method of the bunch. It's using this approximation. So e to the L delta t is approximated by identity plus delta t over 2L, and then multiplied on the left by the inverse of identity minus delta t 2L. Okay, so let lambda, well, okay. Let k be an eigenvalue of L. So then the eigenvalues of the approximate exponential if you think of this whole expression as a function of a matrix L, then the eigenvalues of this matrix function are the same function applied to the eigenvalues themselves. So it's 1 plus dt over 2k divided by 1 minus dt over 2k. What happens to that expression as delta t gets larger and larger? Keep in mind that k is generally going to be large. The eigenvalues of L get larger with the number of grid points. What does that expression tend to as dt gets larger? Yeah, you want to see what happens to lambda as delta t gets what? No. Nope. What?
Becomes negative as if dt is greater than 2, that'll equal 0. There's not going to be a solution for it. If it's greater than 2, it's negative times k.
Right.
So the whole fraction is going to be negative.
Yeah, because what happens is as dt gets larger for fixed k, the 1s become negligible. Yeah. And then the dt and the k and the 1/2 all cancel out. So as dt goes to infinity, lambda approaches -1. So this approximate exponential operator becomes roughly a negation operator. So that's literally why we're seeing the flipping going on. So the solution remains bounded, but then we have this non-physical alternation here. So now we solve a way around that is to either use a different value of theta, or just use a smaller time step. But the thing is, we like using larger time steps, of course, and you think like, well, this is a second order accurate method, so you should get nice bang for your buck, not having to use dt so small. Also, it's unconditionally stable, so you think, oh, I should be able to get away with a large time step for that reason. But no free lunch here. Yeah, so whereas with backward Euler, the equivalent expression, the lambda in that case, is okay. It's just 1 over 1 minus dt times k, and the eigenvalues of a matrix L are negative. It's negative definite. It's a symmetric negative definite. So we have something positive down here, and always less than 1 in magnitude. So that's why it's unconditionally stable, no matter what. Similar idea can be used to explain why why Crank-Nicolson is unconditionally stable. But the point is, we're not going to see flipping here. It's just, since it's less than 1, but also positive, it's just straight out damping, which is what you'd expect for heat. It's going to be slowly diffusing to 0, but it does so in a way that does not cause this flipping back and forth. So a lot of people like to use backward Euler for that reason. It's, again, it's simple to implement, unconditionally stable. But if you have many grid points, then then your system becomes more ill-conditioned, and therefore the solution is less accurate, and so you get problems for that reason, unless you use a smaller time step. So, and every talk and paper I have about KSS methods is why I go on about these kind of methods, conventional time stepping methods like these, that either way, larger time step is going to cause problems. For explicit method like forward Euler, it's going to cause the solution to blow up, like we saw here. For a implicit method, you get non-physical effects like in Craig-Nicholson, or your method for solving systems of equations is going to have problems due to the ill conditioning that's going to ensue as the number of and the problem gets worse and worse if you have a larger number of grid points. So this is stiffness in action. This is what's known as a stiff system of ODEs. That generally is what you get from a PDE. That's why, personally, I think more work needs to be done on the time stepping side, and that's why we have adaptive time stepping methods to automatically adjust in case the behavior of a solution changes. If it's quite smooth, then maybe you get away with a larger time step. If not, then you need to shrink it. It's nice to have to be able to do that automatically. Okay, so any questions about what happened here? Okay. Does anyone have any questions they want to bring up about either assignment? Okay, most likely assignment 1, but oh, okay, yeah, sorry about that. Yes. Okay.
Try to find the error here in this one. It's not coming.
Oh, like it's not doing it, or
yeah. If I
okay, yeah, go ahead and run it.
Without it, it's running perfectly, but the error is not there. Here, error is not there for the OD.
Or it's not printing it or something, or
No.
I'm not sure if I understand the question.
OD23, all the other errors are coming.
Okay.
I put it here. OD23. If I
Okay. Okay. Oh, the shapes are different. Yeah. Okay, so that's a problem right there. Okay. So, alright. So y is coming from here, and oh, you're pressing the wrong t. It needs to be t, not t1.
Okay, here it's exact, no? Isn't it?
Well, yeah, yeah. You want exact solution too, but the parameter, because for it's fine for the plot, but yeah, but down here these vectors need to be the same. So you need to have, since y is the solution evaluated at capital T, the exact also needs to be evaluated at capital T.
Okay, that means.
Yeah. So if you just change this to T.
Okay. I thought.
But also down here, change that. Okay, now it's
because
something else.
because I think I used here T1. coexist.
Well, and that's fine. Okay, so here, okay, but here these t values are different anyway, so it's fine up there, but here, okay, oh, okay, so still complaining about the shape. Also, I'm not sure why I'm doing a transpose. Okay. Oh, okay. So Z. Maybe it's okay.
Oh, sorry, this one. Sorry, this should be hashtag.
Okay. 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 Go ahead and run
Try
again.
it again.
Oh, okay. It's still an incompatibility. Okay. Maybe it's to do with how.
Is it about this y1 exact?
Well, that's what I want to check. Okay. So here it's an array. Oh, here you have T and T1. That's kind of strange. Okay. Well, but these look fine the way they are. As array of lists, but okay. Wait, okay. Where'd it go? Okay. Oh, okay, this. Can you have it print out len of actually, okay, right here. Print out the len of y and len of z. I'll see the length of both of those. In the meantime, anyone else have any questions about any of these assignments? Okay. Unfortunately, I ran out of material for today because of my what I attempted to present today did not work out. But what I'm going to be doing is using what I showed you today to build towards a default project that I can plan to be ready to share with you on Tuesday. If any of you have ideas for what you'd like to do, I know some of you at least are thinking about that. By all means, let me know. Okay. I think we'll just be around in case anybody else has any questions about the assignments.